Here in this example, we actually have a 3D problem. We have this plunger which is moving down, up and down, whose height is given by z. Z is a sinusoidal function in time. In addition to that, the plunger is rotating about the z-axis with a constant rate of omega. And what we want to do is determine the magnitude of the acceleration of this point A on the outer rim of the plunger as it moves up and down and rotates at that constant speed of omega. So let me make a sketch here. I'll make an attempt here at a 3D sketch of that plate there on the bottom of the plunger. Like this, here is point A. The center of rotation of this thing, this point right here, is O, and this is A. So what we're going to do is talk about a radial unit vector of ER. We're going to have a unit vector corresponding to the rotation angle of theta. It's in the plane of the plate of that plunger. It's perpendicular to ER, so it looks like this. And then the 3D nature of this says that we also need to have a third unit vector, which I'll call K, which is always pointing in the upward direction. All the components that go into our expression for A are going to be like they are before, in addition to one more coming from the z direction. So what we have here is R, we know, is a constant. The radius of that disk is a constant, so therefore what we have is R dot and R double dot are both equal to a 0. Theta dot, which is omega, is a constant. So that says that theta double dot is a 0. And z, the height of the plunger, we know that it's this sinusoidal function in time, z naught times sine of 2 pi in t, where n is a constant. So when we take one time derivative of z, we get z naught times 2 pi n times cosine. One more time derivative of this gives us a minus sign sign in front. We have 2 pi n squared, and the sine comes from our cosine. It looks like I left off my 2 here as that. So that's all the pieces that we need in order to put this together. We will say here that A is the usual polar description of R double dot minus R theta dot squared ER. R theta double dot plus 2 R dot theta dot E theta. In addition, we have now a Z component. And that z component is just going to be z double dot, because it's moving in translation in the direction of k. We were given that theta dot, which is omega, is a constant. We were given that r, or this radius of this disk, is a constant, so r dot is a 0. It's 0 for all times, therefore r double dot is a 0. So A has a component here, minus R omega squared ER, plus the Z double dot is going to be a minus 4 pi squared n squared Z naught sine of 2 pi n t, and that's our component in the direction of z. The magnitude of A, well, it's just the sum of the squares with a square root of our components there of A. So this is R omega squared plus 4 pi squared n squared z naught sine 2 pi nt quantity squared, like that. So this is a polar problem with an additional dimension there of z. We have our usual ER component, we have our usual E theta component, but being this is a 3D problem, it's a cylindrical coordinate problem. We have a z double dot contribution coming in on k. In this case, it was just a matter of taking the two time derivatives of z in order to get our k component. In the end, the magnitude is just the sum of the squares with a square root for the components there of a.